Fundamental Theorem of Calculus, Part 1. This is the part that says if we start with a function f and we integrate to get the accumulation function, then the derivative of that accumulation function is the function f that we started with. This is provided that f is continuous. Notice that a is a function of x. It's a variable of this top limit of integration. So a prime of x is f of x. T is just a dummy variable. This is not f of t, it's f of x. Let's start with looking at an example. Let's look at an example where f of t is a really simple function. F of t is constant. It's equal to 3, and this a we'll take to be 2. So our accumulation function will be equal to the integral from a to x of 3 times dt. To figure out what that is, we can use the area interpretation of an integral. We figure out what this area is. That's the integral from 2 to x of 3. Well, the base is x minus 2. The height is 3. So the area of this rectangle is 3 times x minus 2. So that's our answer. That's the accumulation function. That's the answer to this integral. That turns out to be 3x minus 6. Now what happens when we take the derivative of 3x minus 6? Well, taking the derivative of 3x minus 6 is easy. The derivative of 3x is just 3. The derivative of 6 is 0. So we get back 3. That's what we started with. That's what the first part of the fundamental theorem of calculus is telling us. Notice that a of x is this area. It's this area that I've shaded in here. As x moves, that area changes. If x moves this way, the area gets bigger. As x moves that way, the area gets smaller. What we're saying is the rate of change of that area is exactly this height 3. That is, as x moves a little bit, the rate of change is this height. That's what the first part of the fundamental theorem of calculus tells us. Let's look at another example. It's a little bit more complicated. Let's look at f of t equals t over 2. And let's start this one at a equals 0. So again, we compute what this area function is, a of x. That's equal to the integral from 0 to x of t over 2 dt. And let's make a sketch of y equals t over 2 and plot what this a of x is equal to. Well, it's an area that's dependent on x. And to compute it, we can use this area interpretation of the integral. And so the base here is x. That's the base of the triangle. The height is what we get when we plug x into this. So it's going to be x over 2. So the area of the triangle is x times x over 2, all divided by 2, base times height over 2. And so when we simplify that, we get x squared over 4. So that's this area. So now what happens when we differentiate that area? So this says when we differentiate the area, we should get back the original function. And so when we take a prime of x, we take the derivative of x squared over 4. That's 2x over 4, which is the same as x over 2. And indeed, that's the original function that we started with, except with an x instead of a t. That is, we're saying that this area changes as a function of x, and its rate of change is exactly this height, x over 2. That's pretty cool. When we do an integration and a differentiation, we get back to where we started from. That's an important idea. Even though these were examples where we actually knew the integral, notice that we didn't ever actually have to compute it. That is, we never needed 3x minus 6 to figure out this answer was 3. We know the answer is this. That's what the theorem tells us. We never had to compute x squared over 4 to know that this answer was x over 2. That's what the theorem tells us.